Okay, hi everybody. I am now going to go through the solution for Chapter 9, problem number 10. This is a nice, just classic rotation problem. We have an electric fan which is turning off, but initially it's spinning very fast. It's spinning at 500 revolutions per minute, and as it's spinning down, 4 seconds later, it's still spinning pretty fast, 200 revolutions per minute. So for the first part of this problem, it's just referring to that time period from as it slows down from 500 to 200 in that 4-second period. And the first question is, what is the angular acceleration in revolutions per second squared, and what is the number of revolutions, or what is the angular displacement of this electric fan as it slows down? Okay, so before we start anything, we should just write down our knowns as we always do. So the first thing they told us is the initial angular velocity. Right, so omega naught, omega for angular velocity, naught for at time equals 0, is equal to 500 revolutions per minute. Okay, and so neither of these are SI units. Typically, I would recommend you want to convert revolutions to radians, and you want to convert minutes to seconds. In this case, they're looking for answers in revolutions per second squared, not in radians per second squared, and they're looking for the angular displacement, not in angle and radians. They want it in revolutions. So I'm going to keep revolutions in this unit because they're looking for the answer with that unit. But I do need to convert these minutes to seconds, so I'm just going to multiply this by the conversion factor. 1 minute is equivalent to 60 seconds. Right, since those are equivalent, dividing them is just basically equal to 1, so I can just multiply it by this. And my minutes cancel, I get revolutions per second, and I have 8.333 revolutions per second. Okay. They also tell me in the problem that at time equals 4 seconds, right, sometime later, the angular velocity at that moment is 200 revolutions per minute. Okay, so it's still spinning fast, and I can do the same conversion. 1 minute is 60 seconds, and so that gives me the angular velocity at that moment is 3.333 revolutions per second. Okay, so those are our knowns. There's one other known that's kind of hidden in the problem. It says that the angular velocity decreases uniformly. Okay, so that's a good idea to maybe just plot that, right? So initially, I can plot omega versus t. Initially, it's spinning at 500. Sometime later, it's spinning at 200 or so, and it's decreasing uniformly. So what that means is as it decreases, as the angular velocity decreases, it's doing so at a constant rate. So I draw a straight linear line here. All right, so this is a straight line, which means that the angular acceleration as a function of time is some constant negative number, right? And that's what we're actually looking for in part A, is to find that number. But the fact that it says the angular velocity decreases uniformly tells us that alpha is equal to constant. All right, it's some constant number, and what that means is we're allowed to use the constant acceleration equations to solve this problem. Okay, so that's going to be very helpful. All right, so now we can actually get started now that we know about our knowns and unknowns here. So for part A, it wants us to find alpha. Right, find their angular acceleration. Okay, and we can note that since we know the angular acceleration is a constant, that gives us a clue that there are these 4 constant acceleration equations which are available to us and will be helpful to solve problems. We can look at those 4 and recognize that this equation, the initial angular velocity plus angular acceleration times time, tells me the final angular velocity. This will be useful for solving the problem because I know the initial and final angular velocity and I know the time elapsed. I can solve for alpha. Right? And you should recognize this. This looks a lot like this equation from chapter 2. Right? And it's the same idea here. It still applies for angular quantities. I just need to replace acceleration with angular acceleration and velocity with angular velocity. Okay, so solving this, I can solve this for alpha. And I can just plug in. My final angular velocity is 3.333 revolutions per second. My initial angular velocity was 8.333 revolutions per second. And I have to divide that by 4 seconds. Okay, and when I do that, I'm obviously going to get some kind of negative number, and that's what I expect, some kind of negative acceleration. I get negative 1.25 revolutions per second squared. Okay, so I have positive angular velocity, I have negative angular acceleration. That means the object is slowing down. All right, those two vectors are pointing in opposite directions. The change in your angular velocity is negative, right? You're slowing down. Okay, so that's the first part of part A. The second part of part A is it wants to know the number of revolutions made by the motor. So as this thing turns, as it slows down, it is going to turn through a certain amount of distance, a certain amount of angle. Right? So what this is really asking is to find the angular displacement. How much angle is this thing turning through? Remember, theta is our unit now. We're not using x, we're using theta. So this is just how far is this fan traveling in angle as it slows down. Okay, so we want to know the change in the angle. Right? So one of the other constant acceleration equations is theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. Okay, and so this has theta and theta naught in it, right? So I can solve for that. Delta theta is equal to theta minus theta naught, which is equal to the second part of this formula. Okay, and this formula should look very familiar to you too, because we've used this formula 100 times already in this class. And the equivalent formula is just we're replacing our spatial dimension. Instead of using distance, we're using angle. Okay, and so I know everything here. I know my initial angular velocity. I know the time is 4 seconds. I know my angular acceleration now is minus 1.25. So I can solve this plugging in for all those values, and I get 23.3 revolutions. Okay, so that's why we kept everything in terms of revolutions per second and revolutions per second squared up here. It allowed us to quickly just solve for the number of revolutions. So this is just the number of revolutions. If I want to know the number of radians, I just multiply this by 2 pi. Right, that tells me how many radians I've turned through. Okay, so that's part A. Let me just highlight the answers here. For part B, it says, how many more seconds are required for the fan to come to rest if the angular acceleration remains the same as what we found earlier? Okay, so this one should be pretty easy now that we found all this information. And I'm running out of room here, but I think I can just squeeze it in. Because basically this is just saying that now the final angular velocity is just 0, right? It's going to come to rest. The initial angular velocity is what was our final angular velocity before, because it's asking how many more seconds, right? So during the first 4 seconds, we decreased from 8.33 to 3.33, and now that we're at 3.333 revolutions per second, it's asking how long is it going to take to get down to 0, right? So now my initial angular velocity is going to be 3.333. Okay, and it wants to know just time, keeping in mind that our acceleration we know is minus 1.25. So we can use the same equation we used before. Right, we know the initial angular velocity, we know the final, we know alpha, so we can solve for time, and I found this to be 2.67 seconds. Okay, so that's how long it's going to take to go from 3.3 revolutions per second to 0. So for a total, it would take 4 plus 2, or 6.67 seconds for this object to slow down. Okay, that was that solution, so thank you.